In this video, we are going to learn how to model a surge arrestor for EMT. So a surge arrestor is a nonlinear resistance. Typically, nonlinear resistance in EMT type software like EMTP are piecewise linear, and so which means they are fitted with a linear segment. This is what you can see here in green. Whereas for surge arrestor, here we can see the characteristic of a surge arrestor, so the voltage versus current curve. It's actually best fitted with a piecewise exponential, segments, which means that users will enter the VI curve, and then we will use a fitter to determine those exponential segments. Here you can see to fit typical curve, so you have first the linear region, we will come back to that, and then only with like two exponential segments we can fit almost the entire curves, whereas to get a similar fit we will need to see so many linear segments, and which will of course slow down the simulation and even get precision which is lower than what you will get with exponential segments. So those VI curves are also frequency dependent, surge arrestor VI curves, which mean that the voltage for a certain current will depend on the surge rate of rise. For example, you have typically when you do test of surge arrestor or even during simulation, you have surges which looks like lightning and which has similar rate of rise as a lightning surge, and you have switching surge. And so for the same current of this surge, you will have different voltage value, or the opposite, for a certain voltage surge, you will have different current value, which means the surge arrestor is frequency dependent. Now we have several options for modeling. Either we use the VI curve, which has been determined by test surge similar to what the simulation will be. For example, if you're doing a switching study, you will use switching surge voltage and current points to build the surge arrestor model. And if you are doing a lightning study, you will use a lightning surge test results to build the VI curve of the surge arrestor. Typically, the difference between the voltage for both type of surges is about 10 to 15%. So now when you're performing an EMT study, what data are you going to require? So of course the first thing is the MCOV, which is the maximum continuous overvoltage. It is the limit of the linear region. It's the voltage that the surge arrestor can withstand indefinitely. Often it's limited to 10 milliamps of current, and so typically in the VI curve we will put the MCOV at 10 milliamps, and so that will be basically our first segment for the linear region of the surge arrestor. So that's the first thing which is required for the model. Then, according to the type of models you are going to use, you're going to require more or less data. For example, here you may need the switching surge if you are studying switching, or I haven't discussed it, but you can also build a frequency-dependent model of surge arrestor. In this case, you will need all surge tests. So you have the switching surge voltage and currents. It's also called discharge voltages or currents and currents. For example, it could be it have this shape. So 220 kilovolt, those are peak values for 3 kiloamps, peak again of a switching surge. And here you have the characteristic of the surge used for testing. Here it means the voltage rise was in 300 microseconds, and the tail duration was 100 microseconds. At the next slide, I will have a small picture showing that. You have the switching surge can have different shape. See, you can see here several of them. Those are all considered the switching region. So again, if you are going to use a surge arrestor which is not frequency dependent, so just a nonlinear resistance, and you want to study switching, then you may want to take, if you can, of course, use the points of a surge here, which will be similar to what you obtain by simulation. You can go back and forth, of course. It's not necessarily the easiest way to proceed, but that's a solution that provides fairly good results. Similarly, you have the lightning surge, which could be of the shape 820. This is actually a standard shape, or 1.250 micro. So again, those are called the discharge voltages and currents. This one is particular, the 820 for 10 kiloamps. In some IEEE documents, you will see it as being called V10 because it is used in the procedure to build a frequency-dependent surge arrestor model. So keep in mind these values. We will reuse them later in this course. Now, if you need to build a frequency-dependent model, we will discuss that after again. You will need also to know the number of parallel columns of metal-oxide valve elements. So surge arrestors may be built with several columns in parallel, so you will need that for the frequency-dependent model. You will also need the length of those columns. This is a required information. And those two other data we would need here, so the switching surge energy rating and the TOV curves, you will not need them to model the surge arrestor, but more you will need them to process the results. For example, if you do a switching or a lightning study, you will have overvoltages, and so the surge arrestor will conduct. And of course, as the surge arrestor conduct more current, the temperature will increase, so there will be some energy through it. So basically, typically you compare this energy during the simulation with some limits. So those limits are the switching surge energy rating for switching, and typically they are given in kilojoule per MCOV or kilojoule per kilovolt. And so you can then, when you know the MCOV of your application, basically you can know the limit of your surge arrestor and compare it with simulation. The TOV curve is used during temporary overvoltage simulations. For example, single phase to ground fault, load rejection, for resonance. In this case, you must use this limit here, and you shouldn't use actually the switching surge energy, which is a common mistake. Okay, so let's now discuss the two ways to model a surge arrestor. Actually, there is three ways to model a surge arrestor in EMT. The first one being to simply use the piecewise linear, the piecewise linear nonlinear resistance, so the nonlinear resistance, which is piecewise linear, and just enter as many points as you can. Again, often you don't have so many points, and so you may do big mistakes, big errors between what you get between segments, between points and the real surge arrestor, so it's not recommended. Still possible. Then you will have this method here, which is a simplified model. Here you use a ZnO, the ZnO model in the library. I apologize, here there is a little typo. So you use the ZnO model in the library, which is the nonlinear library in EMT. It comes basically with two devices. One is the filter, and then you have the device itself. The goal of the filter is you enter the VI curve, so you enter the point voltage current, and it will automatically find the exponential segments to fit that, as we showed in the previous slide. And then you can copy the data from this filter. It's done by right-clicking and going on copy. I will show you, and then you can paste them inside this ZnO. Same thing, right-click and paste data. And it will automatically populate this device. In this device, you enter all the segments, so with the exponential coefficient. maybe we can I can show you in the MTP how to do that. Here you have some data we can use for the demonstration. So here you have the rated voltage of the surge arrestor, then the MCOV line to. Remember, the MCOV is given in RMS value, line to neutral. Then you have the current switching poles so we'll use those points to create the VI curve. So now we will have a model which is valid for switching studies, and it's a good idea to check during the study that the overvoltage that we get have somehow a shape similar than this one, 3060. Okay, so let me here open EMTP. All right, what I'm going to do is copy here this part so we can have it in the design. And I'm going to paste that here. All right, so first thing to do is to grab in the nonlinear library the two components, so the ZnO arrestor and the ZnO data function. So first thing first, we are going to use this data function to create the segments. Okay, so yeah, I have to save the design. Save that here. All right, so when you double click on this device, you have this thing. So that's the filter. Here you have the field where you will enter the VI curve. Then you have here those two fields which are options to rescale that curve. Basically, these curves are sometimes they are given for a certain category of surge arrestor. But then the surge arrestor you have is another MCOV or another voltage rating, and so you need to rescale this curve. So this is what you can use that. So here you will, in the second field here, you will enter the voltage rating of this curve here. And in the first one, the voltage rating of your application. And basically the voltage point will be rescaled, so divided by this value and multiplied by this one. In our case here, we will enter directly voltage and current. So what we can do here to make our life simple is to put the same value here. So it can be 1, or it can be, for example, 18.8. Okay, it does, so this value here doesn't matter again because all the voltage points will be divided and multiplied by the same value. Okay, then here you have other multipliers. Those can be used, for example, if you enter the curve in per unit, then you use the voltage multiplier to put them in regular, to put them basically in normal data, in volts or amps. Similar to basically what we use here. So you can, it's very flexible, you have in many things. And here you have the minimum current value. So before this value, the surge arrestor is considered linear. So here we can set that, for example, to 0.01, so 10 milli. So here the first point we are going to enter actually is the MCOV. Okay, so the MCOV it's again 10 milliamps, and the value is 15. So it's 15 square root of 2. So here I should calculate that quickly. So it's square root of 2 multiplied by 15. All right, so 21.2. So here again it's 10 e minus 3 and 21.2. E3, of course, we're in kilovolts. So I go from RMS to peak. Then I put those points, so 125 amps for 36.2 E3. I just put a space in between, 538.5 E3. So typically you will have 3 points, 4 points max for this curve. So that's why, again, it's very important to use the exponential segments. The fitting option, you don't really have to touch it here. Same thing for the gap. Here it's ZnO gapless surge arrestor, so there is no gap, but you have the option here to define gap with a voltage, flash voltage. But here it's not the case. So right now it's finished. You have the procedure here, explain how to populate data from the ZnO data function to the surge arrestor itself. First thing, you click on OK, then you click on OK again. Now you see in the console the feeder started and ended means it's successful. Now we so if I don't use this data function and I open the surge arrestor, you'll see here it's empty and I have to find basically the exponential segments. Now to populate the data, you right click on this surge arrestor data function, the data function, you go to copy data, then you go to the arrestor, and you go to paste data. Now when you open the surge arrestor, you will have all data populated here, so you don't have to do it yourself, and it's now ready to be integrated to the circuit. It comes in a single phase version, or if you right click and go to three-phase signal here in line type, or if you connect it to a three-phase signal, it will automatically turn into a three-phase signal. So this is for the first model, the first surge arrestor model, the simplified version. The second model is what's called the IEEE frequency dependent model. Again, here, sorry, I put twice IEEE. So this model is frequency dependent. It has been defined by the IEEE Working Group 3411 on surge arrestor model. So basically this model is an aggregation of several models. It actually looks like this. It's an aggregation of several devices. So you will have two nonlinear resistance, which are exponentially fitted, and an arrangement of RLC circuits. So this is the surge arrestor. It's kind of a small circuit, but this is the model 1 surge arrestor. And in this procedure, we will basically adjust all the RLC components as well as those two curves to fit the switching and the lightning curves. So what you're going to need to build this model is the V10 I was talking about, the 10 kiloamps, 820 microsecond pulse, and any switching impulse test. It's also good to have a third impulse test result, like a lightning one, just for validation purpose. So we'll use the V10 and the switching impulse test fitting, and then it's nice to have a third one for validation of precision. You will also need to know the number of columns, the surge arrestor, and the estimated height of the surge arrestor. Okay, so now how do you calculate all these elements? Well, the equations are over there written. So D is the length of the surge arrestor, and is the number of columns in parallel. Here, what I really recommend you to do is go on our website to the Exchange platform, and you have two resources you can use. The first one is a guideline example where we basically walk you through the procedure to build this surge arrestor model. And then we also have an add-on you can add to EMTP. You install it and you can add it to EMTP. And in this case, you can it does all the job automatically. So here in the guideline, you have the procedure step by step, which are also in the EMTP design. So the first thing to do is to adjust those two nonlinear resistances. The shape of those curves are standard. The only thing we are going to change is the scaling. So what we are going to use is the desired voltage rating. You basically reuse the curve that is provided in the guideline and enter here your V10. So V10, which is again the 820 10 kiloamps impulse test. Then you create the fitting. You do the fitting for those two, A0 and A1. So you do this procedure twice, and that will be your first step. The second step will be to simulate the switching surge. So you are going to bring your surge arrestor model assembled like here with the correct A0 and A1 and the correct parameter as specified here. And you're going to connect it with a switching surge current source from the source library in EMTP. From this source, you have to enter the peak current, not the peak current actually. This is a double exponential source, so you have to enter the magnitude current of the double exponential and two parameters, alpha and beta. Those parameters can be a little tough to find, but very often you don't have to be extremely precise for that, so you can use the following estimation, simplification. So if your impulse test is 300, 1000, just take the inverse like that for beta and alpha and enter those values in here, like it's done. Then you do the simulation and you visualize the voltage at this point, and you compare it with the impulse switching surge voltage you are supposed to get. And the ratio between those two, you enter them here in voltage multiplier. And regenerate A0 and A1. That way, when you resimulate that a second time, you should get exactly the same thing as the voltage surge. So in this step, we adapt A0 and A1. We rescale A0 and A1 in order to match exactly the voltage of the switching impulse test. All right, so then the last step is to do exactly the same thing as that, but now here to simulate V10. So to change alpha, beta, and the magnitude here to fit the 820 microsecond 10 kiloamps impulse surge. Simulate that, and then we will adjust L1 in order to match V10. Typically, when you decrease L1, it will increase the voltage you get. Okay, so you just go back and forth. You can do a dissection, or you can do step by step until you have a match that you like. And so that's pretty much it for the procedure. Once you're there, the model is finished. It has been validated for switching. It has been validated for lightning. And again, you can try it with other type of impulse if you have in the catalog, and you should see it is working well. This IEEE model should be used only for lightning or switching, but mostly lightning. It shouldn't be used for lower frequency. It's not valid for 60 Hertz or a lot lower, so don't use this model for low frequency. For low frequency, you'd better to use the previous model we showed, or no model at all often. When the voltage doesn't go so high, like for TOV, the surge resistor model isn't needed. But if you still want to put the surge resistor model, use the previous model just with only one ZnO device. If you do a lightning study, make sure to model also the lead conductor connecting the surge resistor to the ground. This has an impact also. You can use, for example, an inductance for that with 1 microhenry per meter. This is typical. All right, so let me go through this example. So again, everything is explained in here. So let's say you have a new surge arrestor you want to build. So you open this example and you just change the value. So you double click on the mask and you have all the parameters you can modify here. So you enter here the height of your surge arrestor, the number of columns, and all the rest will be adjusted automatically. So just those two things. You go inside, you will notice the model, and you go from those two, you change the desired voltage rating, click on OK, and then do the copy and paste here. You do the same thing for this one, you change this value, click on OK, and do the copy and paste. Now you have your first version of the model finished. You bring this first version over here, and you do the simulation. You simulate here. Yeah, like I said, you drag and drop. You bring this the current source. The current source, you see the equation is written there. Alpha and beta can be calculated like I explained. Alpha will be the inverse of the tail duration, and beta will be the inverse of the rise time. This is an approximate value. For IM, usually what I would recommend you to do is first take a put, for example, 10,000, run the simulation and look at the current, and then adjust it to match whatever peak you want. And so we can do it together. So I put here 10,000. Now I simulate this. Going to open scope view. Again, all the procedure I'm showing you now, it's if you decide to do this job manually. If you prefer to, but you can also have this automatic add-on, which does the job automatically, basically. So you don't have to do all that. I will show you that after. All right, so here you select you look at this name is iSurge1. Okay, we see now the peak is 4,200 approximately. We want 3,000, so what I do here is I do that equal 3,000 divided by 4.2. Okay, and that will rescale nicely the current shape. And I know now this is the real. Okay, you see it goes to 3,000 now. This is the real impulse test that was used, current impulse surge, sorry, which was used during the test. And now I'm also looking at the voltage at this point. So I will go to branch voltage of surge 1, and I see it goes up to 225 approximately, which is the switching impulse test. In this example, the job has been done already, right? Here, those things have been modified. If you put 1 here, by default it's 1, the voltage multiplier, you will have here something like 229. Then you do 229 divided by the value you want, 225. Then you take the inverse, and that's what you use for the multiplier, just to adjust the voltage. Okay, and so lastly, the last step. So we take here this curve, the second surge, which is the 10 kiloamps at 820 microsecond. You can reuse this one, it's a standard one, so this one you don't have to play with the parameters. And you adjust L1. So by default, N1 here was 15. So I run the simulation as if we haven't modified it yet. And you see that with this value, okay, the peak we get is 263. We are looking at 248, so we need to adjust that. And so that's why you can go step by step. For example, first you can try with 10, run this simulation. Okay, here obviously I know the answer, so I will go very quickly for the presentation, but when you're alone, we go a bit slower. So you see the voltage here decreased, and if now I go to the final value, which was the correct one, can run the simulation one last time, and okay, now you see it goes exactly where we want. The peak here is 263. Perfect. All right, so this is the procedure described by IEEE. Obviously, we simplify your life. So we created here an add-on. When you install it, it will bring a new toolbox here. And the device you want to use is this one, the IEEE FD arrestor, which is exactly what we've done here. When you double click on it, you can now enter directly all the information that was required. Number of column, the length of the surge arrestors, the impulse test you are going to use. So the current for the switching test, the current for the lightning test. So this one, remember, is standard, so you should always keep 10,000. Then the discharge voltage for the switching, the discharge voltage V10 for lightning, and then the alpha and beta for the different tests. Again, for lightning, so those two are standard, you don't need to change them. So you enter all that, and when you click on OK, it will oops, actually, when you check this box here, it will automatically run many simulations and do everything we've done manually. It's going to do it now for you. So you just have to be a little patient and wait. You can follow here what's going on in the console. This may take 2 or 3 minutes to do the whole job, but then it's finished. So let's follow together. Here you see we have adjusted IM to get the good current of 3000. Now we run the simulation. We see that we adjust now the magnitude of A0 and A1 to match, so that we can see the same 0.994 that we obtained with the manual approach. Now the last step is to simulate the 10,000 amps and adjust L1. Okay, so here the goal will be to find 248,000 volts, and we try with different value. The first value of L is written here, and you see the errors. Okay, so you just basically wait until convergence. All right, so now if we take a look at our model, everything should be set up properly. So all that should have been adjusted, and you have your multiplier in there. All right, so well, that's finished for the modeling of the arrestor. You just now how it looks like inside a circuit. So you see here we have a little a switching study with like 2 surge arrestors here and here. So one thing that often you do when you do a switching study is, well, first to determine the maximum voltage. Second is to determine the energy through the surge arrestors. If you want to do things very well, you should actually use 2 different models if you do the voltage mitigation or the energy absorption. The thing is, when you have your catalog with voltage current curves, you have some precisions in data. And when you do the study to find the maximum voltage you get, you should take basically the curve which for a given voltage level have a lower current. And that will give you the worst case for a switching study. And now if you do energy absorption, it's the opposite. You will take the VI curve where for a certain voltage level you have a higher current. And that will create the maximum energy. So how do I check the energy here through the surge arrestor? Well, you have two solutions. The first one is obviously to just connect here a power meter. Connect the power meter here and to integrate this energy. To integrate this power, to get the energy. All right, so you can simply put here a scope. And so that's one option. The second option is actually if you go in the mask and you go to observe, you can here select the energy directly. So I don't know if you guys you're familiar with that. So there's a little the way to do that. To do that is explain how to get to this signal. I'll show you here quickly. So you select those boxes, then you bring a meter, a control meter, a control scope. You draw a bit of wire and you name this that way. So you write name, you put it visible, and you put E underscore, then the name of this surge arrestor and the phase when it's a 3-phase device. And so now automatically it will take here the E. So that's what is explained right there. And you may do that for the 3-phase. So here, obviously, this energy is 3-phase. If you want to do it phase by phase, you need to do this procedure per phase. Here you will have the energy per phase in scope 1. Well, let's take a look at that and check in scope view. Okay, so first let's take a look at the voltage here, L4M. Okay, so we have here the voltage when we switch. So you see it goes pretty high compared to 1 per unit here. It goes probably to 2 or a bit more than 2 per unit. Now let's check scope 1, which is the energy. Right, and so we see the energy rising. It doesn't go so high, but it's rising. And then the energy right here. Actually, scope 1 was probably not the good choice to visualize because the voltage is not so high on phase A, which is the blue one. Let's go on the phase C instead of A. We will probably see more energy going through. Obviously, when you do a study, you do that for the 3-phase. Actually, I don't have to be so lazy, and I can do it here quickly. It's really not so bad. All right, so phase C is, I believe, okay, so if we now compare, it will be pretty similar. So the red curve is the 3-phase energy, and the blue curve is the single-phase energy through the surge arrestor. So you see the end, it's almost the same thing. All right. One reason why we have this slope here, probably I didn't use the good power meter. I took the power meter which is averaged. Here I should use actually this one here, the power meter with a lowercase p, which doesn't use any average. This one is single phase actually, so it's good for what our application. We can here use the bus to ABC to get single phase signals. Connect that here, and then connect those back. Well, you see that it's in the end. It's in the end faster to use this approach, but the two approaches are possible. Okay, so now I'm monitoring here the energy on phase C. Then we get exactly the same results. Okay, so this is for switching. For lightning now, for lightning it's very similar. So you connect here your three. Here we cut the 3-phase, the 3 arrestors in 3 because it's important to model the length of each conductor. So often the 3-phase are not exactly next to each other. There is some conductors in between and the neutral and all that. Everything should be modeled. When you have a surge arrestor connected to an apparatus, you should model for lightning, you should model the conductors in between as for lightning, because lightning is so fast of a phenomena, you may have voltage differences between 2 given points in the substation. Also, like I explained, the lead wire, okay, for the ground wire should be modeled, and the grounding as well. Okay, so if I go inside here, it's this same surge arrestor. You see that we put the small energy meter to monitor the energy. All right, so that's pretty much it for this video. I hope it will be helpful for modeling your surge arrestors. If you have any questions, please feel free to contact us through support, or we have tons of help on our website, or even you can ask questions through the EMT community. Thank you. Bye-bye.